Am I okay?
Yeah.
So first of all, let me just define the concept of structure function. So on the left-hand side, we have electron scattering. Everybody knows this, the two structure functions, F1 and F2. And then there's an alternate description in terms of transverse and longitudinal scattering. The two languages are equivalent. And F1 is almost all transverse. And F2 is transverse plus longitudinal. And there are relationship between them. And people talk about the ratio of transverse to longitudinal. So here the relationship between F1 and sigma t. So F1 is purely transverse, and F2 is purely longitudinal. Now, the F2 is the sum of longitudinal and transverse. And since R is very small, a lot of times people use a mixed notation where they use F2 and R. So here's a mixed notation for neutrino scattering, which also has another structure function, XF3, and they use F2, and then use R, which is from the other notation, because the high Q square R is supposed to be small, but in general, R is supposed to be much less than 1, you know. Maybe it can be a half or a third when it's big. Now, one thing which is nice in this description is in QCD, F2 is related to the sum of the quarks momentum, the fraction momentum carried by the quark, not F1, F2. So in a sense, if you write everything in terms of F2, QCD, they like to calculate F2. Although it looks like a sum of transverse and longitudinal, that's the way all the QCD equations are written in terms of F2.
Isn't it important to point out that R for neutrinos is not the same as
Sure.
R for
Right.
electrons?
Well, this is, whenever I talk about any structure function, they're separate, axial, and vector. Okay, now I will need to also talk about elastic scattering, although it's a talk about inelastic scattering because of some rules and things like that. So there's a direct relationship, and let's talk about free nucleon. There's a direct relationship between the structure function and now yet another language, form factors. And these are the relations of W1, which is purely magnetic, W1 proton, neutron. W2 proton elastic is a combination of GE, which is longitudinal, and GM, which is transverse. And we will use this relationship later. And then for neutrino scattering, you double everything, and there's a W1 vector, which is related to this one, GMV, and W1 axial, which has an FA. And then W2 vector, which has an FV, and W2 axial, which has FA. And then FA is given approximately by the dipole formula. And FV is a linear combination of G, V, and GMV, which is a linear combination of the differences of the neutron and proton form factors. And one thing that you notice right here is that when you go to Q squared, and tau is Q squared over M squared. But if you translate this to one more language, which is transverse and longitudinal, then axial longitudinal is 0. Axial transverse is related to FA. Vector longitudinal is related to GE. And vector transverse is related to GM. So one thing to understand, to see, is when you go to Q squared equals 0, tau is Q squared over 2M squared, 4M squared, so this is 0. So FV is equal to 1, because this is GEV. But FA, when you go to Q squared equals 0, is minus 1.267. So when you square it, it's like 1.6. So you see that the Q squared equals 0, FA is not equal to FV. So this is because actually not equal to vector as a low Q squared. But if you go to high Q squared, FA is pretty close to FV. I mean, what I mean by high Q squared is Q squared half of 1. I'll show you. So since we talk about what we're going to do in the future, we took all these measurements at SLAC, not at SLAC, at Jefferson Lab, on both deuterium, hydrogen, various nuclear targets. And the idea is we use those measurements in conjunction with all previous electron scattering measurements to extract vector contribution to the structure function and try to understand quasi-elastic, resonance elastic. But the work I've done in modeling the neutrino and electron structure function was done before these data were available. So none of these data have been incorporated yet into the Bodek-Yang model. But there was plenty of other data. But we can go back now and look at things more carefully. And also, this particular data has a lot of nuclear targets, so we can really study the nuclear corrections that we will need for Minerva because the two experiments are in a similar energy regime and similar Q-square regime. OK, so what are the issues? This is a neutrino experiment, low energy, low Q-square. So you want to make sure that whatever you're modeling works at low Q-square. So what are the issues of modeling for Q-square less than 1? First, we need to model all the processes for vector structure function for free nucleon for all Q-square and nu using electron scattering data on hydrogen and the deuterium. So this is the first thing we need to do. We need to know what the cross-sections are. And then, OK, we want to predict neutrinos for hydrogen and deuterium. V is equal to A at high Q-square. How much is V different from A at low Q-square? By gauge invariance, the structure function F2 or the vector structure function for all inelastic processes must go to 0, Q-square equal to 0. But this is not required for the structure function. So this low Q-square constraint needs to be modeled for both axial and vector. But at vector, at least we know where it's supposed to be. We need to model all the nucleon modifications when the protons are bound in the nucleon. And then how are those nuclear modifications different for vector and axial? So we go from things that you have lots of data to, and you know very well, to things which you know less well, to things which you really don't know at all. So each time you have to make an assumption, and you have larger uncertainties. All right. Is it really possible to model elastic scattering at low Q-square? Well, people say, well, just use partial distribution function. PDFs are well known. We have several PDF groups, GRV, MRST, CTEC. And from there, you can calculate both electron and neutrino scattering using the quark coupling. And the PDFs have been fit to high Q-square data. But when you do QCD evolution, you start at Q0. And for example, GRV98 was started at Q0 equal to 0.8 GeV. You do fit high Q-square data. But in your equation, it's a structure function which can evolve from Q-square equal to 0.8. So supposedly, you're measuring everything at Q-square at 0.8, which is kind of a strange thing to do. But it's not as strange as recently when the LHC experiment, Atlas, supposedly has measured the strange quark distribution at Q-square equal to 2 by evolving all the way from the collider energy down. So, OK, well, QCD evolution is not enough. It breaks down at low Q-square. You have higher twists, effects become large. All QCD sum rules break down. For example, energy momentum sum rule, which is the total momentum carried by the quarks and gluons equal to 1. That's very nice to have. It has large QCD correction and blow up at low Q-square. Another beloved sum rule that we have, we measure the NUTEV, the gross to Allen-Smith sum rule, which means that just the total number of valence quarks in a nucleon is 3. Also has large QCD corrections. For instance, it was measured at the Q-square equal to 1.7. But if you look at the prediction, it's 3, but not really 3. 3 minus alpha sub s squared over pi plus another alpha sub s squared plus one of the Q-square term, which, of course, blows up in your Q-square as you go to very low Q-square. So you don't really know what's going on. And even the alpha sub h term blow up because you got 1 over log Q-square. So it's a problem. So let's continue with the sum rules. Leading order pattern distribution are fit to high Q-square data, assuming QCD evolution. But they neglect the higher order QCD term and the low Q-square higher twist effect. And in leading order, for example, the GLS sum rule is satisfied by the leading order PDF. All the higher order corrections are ignored. So you say, oh, OK, fine, let's just use. And people at Minerva told me, well, when are you going to switch Bodek-Yang to next to leading order, next to leading order? And I say, never. Because you say, well, can we use these things? You can blow up even faster as you go low Q-square. Or then next to at least the PDFs don't blow up for GRV. The sum rules blow up, but the PDFs don't blow up. The PDFs blow up. So you can't really use these because none of those corrections make any sense when you go below Q-square equal to Q0 square. So the only thing we have is leading order PDFs. And we know that to describe all inelastic data have high Q-square because they were fit to those data. But when you use them at low Q-square, they're not going to work very well. So how do we model low Q-square to a level of few percent if there are so many corrections? Yeah?
Why do you want to do that anyway?
Because we want to describe inelastic scattering for neutrino experiment.
Yeah, but why couldn't I take all the vector information from electron scattering analyses like made?
You don't have any parameterization of everything that works at all Q-square. People always restrict it, and you have to get XF3, and so the language of quarks and anti-quarks allows you to predict neutrinos and antineutrino electron scattering by themselves without a quark language and without separating quarks and anti-quarks, which you do from PDF fits, doesn't allow you to do neutrinos and antineutrinos.
What I'm really after is to make it extreme. Take the delta, the lowest line resonance.
The delta, this doesn't, no, the
PDF is obviously
correct.
hopeless, huh?
I know, it's true. That's why I separate into resonance and inelastic. I'll talk about the delta.
Where do you make the cut between sort of
I'll just,
resonance double? What I was missing is not only Q squared, but I think
W
should be an order parameter
yeah.
somewhere. Huh?
Yes, remember, this is the inelastic in the continuum.
Okay, so you're above 2 GeV.
Above 2 GeV, but we'll see.
Okay.
But we'll see how far below 2 GeV we're going to push it. Okay, we'll try to push it as far as we can. It only works at 2 GeV. We'll try to push it as far as we can. So the first time we did it, it was 2 GeV. Second time, we try to push it.
But then this is different than the so-called Gini definition of DIS.
That's
where
right.
it goes all the way down and continue underneath the resonance.
Yeah, I don't know about that.
You're not trying to talk.
No. I'm trying to describe the cross-section. It's actually. Okay, so the way you try to get the PDFs to work at very low Q-square is to modify them with corrections. And in order to modify, there are two ways to do it. First of all, of course, at the end, you have to fit to data. But when you fit to data, you have to use some sort of function. I mean, QCD does the QCD evolution for you, so at least you took care of that. But then you need to put all those other higher order corrections. So for the first thing you know is by gauge invariant F2 for all inelastic processes may go to 0, the Q square to 0. And the PDFs, so the structure function cannot blow up. And of course, the PDFs do not make any sense below Q square to Q0 square. So you freeze the PDF at Q square equal to Q0 square. And you could, for example, multiply by K factor. We all know about K factors in QCD when to account for higher order corrections. And if you want to go to Q square equal to 0, the K factor should take a form Q square over Q square plus C. And you can say then you can go ahead and use low Q square electron scattering data to fit C, and then the structure function will be 0 by definition. And when you do that, you find C is equal to 0.18 GeV, which is pretty small. But is this the right functional form? Is it the same for U and D quarks? Is it the same for valence and C quarks? Is it independent of X? Is there any theoretical motivation for this form? And there's one more check you can do, is that not only the structure function have to go to 0 as Q square equal to 0, but they have to be directly related to the photo production cross-section by this formula. So F2 at Q square equal to 0, which of course is 0, but it has a factor Q square. Q square times something. If you divide by Q square, you're supposed to get for neutron and proton the photo production cross-section. So that, of course, if you use this form, definitely predicts C, because C automatically becomes. So you do have one more constraint, which is the photo production. Okay, this is great for the vector structure function. What about the actual structure function? We need constraints that apply to the actual structure functions too. After all, this is a neutrino experiment. Okay, before we go to the actual structure function, let's be the additional constraint. Okay, so you can go around to Q square equal to 0, but the PDF is a function of X and Q square. And X equal to 0 means that for all nu, you have 1 point, X equal to 0. Q square of 2m nu. So, but you know that you're supposed to predict the photo production cross-section, which is a function of nu. So you can't use PDF as a function of X and Q square. They have to be a function of Q square and nu. So solution number 2 is maybe use a scaling variable that doesn't go to 0 at Q square equal to 0, and then you can use it to predict photo production. Say you replace it with xw, which is q squared plus b over 2m nu, and you can use the data to fit for the parameter b. And if the photo production there, and if you get the photo production cross section as function nu, then that's great. But is this enough? And is there any theoretical motivation for this particular form? And also, okay, so we have those two. We worry about low Q square photo production. But what all the other things we forgot? Higher order QCD correction, target mass effects, higher twist effects, which are important at large x. So far, we only talked about low x, low Q square. What about large x at low Q square? So what you want to do is first you want to understand what's going on using and try to have all the tools at your hand that tells you what is really going on in the transition region between high Q square and low Q square. Nice thing is Adler sum rule. The Adler sum rule in QCD is just a statement that the number of U quarks, which is 2, minus the number of D quark, which is 1, is equal to 1. And you can measure this number using structure function. You can measure it in neutrino vector or neutrino axial structure function. And the sum rule is either neutron minus proton, or vector and axial equal to 1, or it's F2. If you just use a proton, then you have F2 proton on antineutrino minus F2 proton on neutrino equal to 1. These are all three are at the sum rule. One thing which is very nice now is, unlike the QCD sum rule, the other sum rule is exact. It's a current algebra sum rule that is valid at all Q square down to Q square equal to 0. So finally, we have something that has some structure functions in it, and it says it has to go to 0. It has to go to 1. The difference has to be 1. Okay, so you say, all right, if you but what's typically done, if you separate the quasi-elastic part, F2 has quasi-elastic, resonance, inelastic. If you separate the quasi-elastic part of the other sum rule, you get that the difference between W2n minus W2p vector is minus FV square, and FV square is given this form. And one thing you see right away is that Q square equal to 0, G is equal to 1, tau, this is 0, so 1 minus 0 is 0, so the sum rule is satisfied that Q square equal to 0. The axial part of the sum rule is W2 minus proton, neutron minus proton is equal to 1 minus FA. At high Q square, this is 0 because Q square is very large, so you get 1. Similar this, at high Q square, this is very small, the form factor is equal to 1. But at low Q square, you get minus 1.2767 square. So that's some problem at Q square equal to 0. So at high Q square, it's just QCD sum rule. So you say, okay, well, I'm just going to multiply the structure function by 1 minus this factor, and by construction, then the structure function was obey at the sum rule, except possibly for this FA at low Q square, which is a problem. But let's see how far the problem, where the problem takes us. So here's the other. This is 1 minus FV square and 1 minus FA square. So and these are at high Q square, it's 1. So the correction to the inelastic structure function is small because so the structure function by themselves satisfy the Adler sum rule because the elastic plug is very small. But you see that these two factors are very similar for vector and axial. And of course, axial goes to 0, Q square to 0. So above Q square to 0.2, the vector and axial Adler sum rule is very close to each other. So from this, you can infer that if I'm going to have a problem with the axial structure function and they don't have to go to 0 at Q square to 0, all the problem is going to be here, which is nice to have. It's nice to know that we know right here that vector is equal to axial because it's quarks, but lo and behold, the sum rule says that it's the same for vector and axial down to Q square to 0.2. So we have an idea as what does low Q square mean for as far as axial. Low Q square means Q square less than 0.2, which is not so bad. So now let's so you say, well, what happens for Q square less than 0.2? Now, if you read the paper by Pascos a few years ago, he he studied the Adler sum rule, and he saw all these, and he puts in all the resonances and stuff like that, so you can have everything. And lo and behold, you find out when you go to q squared equal to 0, the elastic Adler sum becomes minus 0.6, but the delta is just the opposite, cancel it, so you're back to 0. So if you take the delta and the quasi-elastic together, it works. And this tells you there's something special about the delta, as you say. There's a lot of things special about the delta. It's isosceles equal to 3/2, or 1/2, a lot of things special. We'll get back to the delta. All right, so fine. So we know that the Adler sum rule works, and it works very well down to q squared equal to 0.2 if you do, but it's just a difference between u quarks and d quarks. So the q squared dependence of the u quark and the q squared dependence of the d quarks don't have to be the same. It's just a difference that has to follow this function. So you want to know, is there a difference between, say, and these are valence quarks, the C cancels. So is there a difference between u and d quarks? So one thing you have to be in this field, by the way, the Adler paper, I think, was 1967 or something like this, right? Very old, okay? But he's still alive, I think, isn't he? Barely. Anyway, so you have to know a lot of history, but luckily I'm old enough to know a lot of history. So 1998, a talk given by Cruz Alan Smith, and of course I was a student I was not even a student there, I was a professor. He says, Gottfried noted that the breathtaking, crude, naive three-quark quantum model, this is a history, so this wasn't like 1967, that by closure of this particular relationship for the operator, the correlations usually, by closure approximation, the correlations vanish, and you get this very nice formula that the integral for W2 EP d nu over q, d nu is 1 minus g, 1 minus the elastic form. So almost the same as the Adler sum rule with 1 minus the elastic form. This is the elastic form factor from electron scattering, except this is naive three-quark particle model. And we don't have a three-quark particle model. For the proton, we have quarks plus valence quark plus C. But at least we know the sum rule, what the sum rule is from the Adler, from closure, for the three quarks, valence quarks. And sorry, this is Gottfried, right? This is Gottfried. So then, but then Gottfried worked a little more on it, and then you have something which we call nowadays the Gottfried sum rule, because you say, well, let's cancel out the C by subtracting protons and neutrons, and then you get this sum rule, which is 1/3 from the valence quark, and this correction, which has to do with the fact that the U bar quark and D quarks are different. That's what we call nowadays the Gottfried sum rule. But if you just look at Gottfried's naive calculation for the three valence quark, he has a somewhat different K factor for the valence quark. He has this K factor. Now this is kind of interesting, because if you look at this, this is a W2 elastic for the proton. If you go to q squared equal to 0, this is just GE squared. And so GE squared is just a dipole. So if you take 1 minus W2 elastic, which is 1 minus the dipole, and you expand it, you get q squared with 0.178. And I just told you when you do a fit to electron scattering there, you get C is equal to 0.18. So there's a relationship between the vector mass and this parameter C through this Gottfried type sum rule. All right, so this is what the Adler sum will tell you should be the difference between U and D quark as a function of q squared. And this is what the green one is what the Gottfried said it should be for the proton. And this is just the dipole form. So obviously,
what's on the axis? Q squared and
q squared. Q squared.
Yeah.
So at high q squared, the elastic form factors are 0, and everything works. All those things work fine. But then log Q squared, they have to be reduced to account for the fact that the elastic increases, so the sum is conserved. So you can say this is a k factor. So as in our analysis, we said we have to have the k factor for u and d quark be different. So I just use the form 1 as g dipole, which is this term, and put in some factors here to account for the fact that u quarks and d quark, log k factor should be different. They all satisfy the photoproduction limit, and the data should tell you for neutron, for deuterium, and the data for hydrogen will tell you that there's a difference between them, and it will work out if you just fit it to the data. But now you have at least a justification as to why you're doing this form. It doesn't come out of the blue. It has some theoretical justification, meaning. And so I'll talk about the fits later, but if you just do the fits, actually you get the d valence to have this pink one, and you have the u valence, this blue one, and you fit hydrogen and deuterium there. And if you take the difference, you get this curve right here, which approximately follows the dashed line. After all, the other sum rule is from 0 to infinity. And we're not integrating over infinity. Our data doesn't go to nu equal to infinity. All right. So we talked about the log Q square part and how we're going to handle it. And we have a good understanding of it from the other sum rule, from the Gottfried sum rule, from the photoproduction limit. That's very nice. So we have the log Q square covered. But what about higher twist and target mass and all that other stuff? So I will talk about effective leading over PDFs. We want to use GRV98 because they work for high Q square, so automatically everything will fit at high Q square. Now, but x and Q square are only variable that work. X is only the fractional momentum carried by the quark at high Q square. When you go to low Q square, you can do an energy conservation principle, and I've done it actually before. And you find out that the variable c, a complicated c, which has the form 2q prime square over q square plus this, and q prime has a final quark mass, initial quark mass, and final quark mass, initial quark mass, and quark pt. So this is the true scaling variable for a quark which is bound in the proton. And if you assume that the masses of initial final state quark is 0, and if you assume that the quarks have a pt equal to 0, this variable becomes a familiar, what we call Georgi-Politzer or Nachman or target mass variable. This is a familiar and beloved target mass variable. But this is the more general formula. And for the case of charm production, MF is not equal to MI, so it takes care of charm production when you scatter neutrinos and you convert, say, an S quark into a charm quark. So the two different quarks in the initial and the final state have different masses. This is taken care of by the scaling variable. All right. So this scaling so now we have the scaling variable. I just copied it. So what we've done is, I said this is too goddamn complicated, and it's actually pretty simple. I mean, it's not just 3 quarks bound in a proton. There are gluons and all that other stuff. So you can't take it that seriously. So I will just add a term. So I know that I will just assume the initial quark is mass 0. Final quark is, say, for charm, we'll have a final quark mass. We'll put it over here. If it's not charm, we'll put it in 0. And I'll lump it all together. I'll lump all this to one parameter, B, which I needed before to get the photoproduction to work. So this B sort of takes care of all this mess here on average. And actually, the final quark mass may not be equal to 0. There are all kinds of gluon emission, so maybe it has some effective mass. So anyway, this effective mass will be taken care of with this parameter B. And these are two ways to write it. But this one allows you to see that this CW becomes X at high Q square, and this CW becomes the Nachman variable if you assume B equal to 0, i.e. you go away from photoproduction. And the other thing you do is with it is I say, well, this takes care of all the target mass. That's nice. So now we have all the target mass higher twist corrections are taken care of. I don't have to worry about the fact that the protons are bound that the quarks are bound in the proton. That's taken care of. That's great. But there can be other higher order corrections, so I'm just going to enhance the target mass with another parameter A, just to account for everything that at higher order, because at higher x, there are all kinds of higher order QCD effects, not just target mass. So it has to be enhanced. So this is a justification for those two parameters, A and B. And supposedly, if it works, then you've taken care of everything. So it turns out that it works. So what we do is effective leading order PDF means that you take GRV98, you freeze them at Q equal to 0.8, but you substitute CW for Xi for X to reflect the fact that at low Q square X is not the fractional momentum carried by the quarks. That's one thing you do. And then you have those K factors we talked about that are satisfied by the constraint of the other sample, the quad fit, and yielding the correct photo production cross section.
How do you calculate structure functions using this PDF?
Just sum of quark charges times just U.
Just leading order.
Yes, everything leading order.
But the target mass corrections also imply that you have to do something with PDFs, not only with the scaling variables, but also
yes.
PDFs when you calculate the structure function.
True, but I've looked at it, and we've done a lot of target mass calculation, and it turns out that the scaling variable effect is the biggest one. The other effects are there, but they're small. Yeah, I've looked at it. The dominant effect when you do target mass is X to Xi. There are small corrections for W1 and W2. They give you an R, yes, but they're smaller.
Small in all kinematical regions, or
yeah.
No?
Yeah, because target mass is only high X. With low X is 0. Okay, so this is the original Bodek-Yang model, which is implemented in the neutrino Monte Carlos. It has only 5 parameters. New scaling variable, a K factor for the valence quark, and a K factor for the C quarks. And that's it, you know. And then you don't include photo production data in the fit. You check, does this predict the photo production cross section? So you just fit everything else, and you say my photo production is a check. And when you do that, you get the photo production cross section correctly. It all works. So the original fit has 5 parameters. Here it is. This C and valence is F2. This is the scaling variable. 2 parameters here and 3 parameters there. And with this, you can fit everything, all HERA data, SLAC data, BCDMS data, JLab data, and the inelastic regime for W greater than 2, down to photo production with a chi-square 1235 to 1200. And that's what we did first.
Just a
Yeah.
shameless question. Do you have you've fitted all this data, which is fantastic.
Yeah.
You've gotten a reasonable fit.
Yeah.
Do you have errors on these parameters as well in this paper that would then therefore span the errors on the data?
Well, we have errors, but this is like a first fit, then we went to a second fit. So, I mean, this is just the beginning.
Well, sure, but in addition, but that is also provided in the paper?
Only for the second one, because it was an intermediate steps. I mean, because we knew that this particular fit doesn't take care on a difference between neutron and proton, because I use only one K factor for the valence quark. So if you wanted to use it for hydrogen, it won't. It's not as good as a car. So, yes.
So this is a fit, so to say, to all these inclusive data.
Yeah,
right?
all of it, yeah.
So what, if you plug it into a neutrino MC, then what do you do with that? I mean, you want to know
You
to what particles these states decay.
I'm still at the cross-section stage. This is the cross-section state. Final state particles, since it's so controversial, it's been delayed till later.
What come during your talk?
Not my talk.
Oh, not your talk.
No, no.
But then I still wonder, what do you do with that in one neutrino?
You generate the event.
Yeah, fine, inclusive.
Yes,
But that's not an event.
that's right. And here it's not so bad, because here's inelastic, and we know quark fragmentation. We've measured quark fragmentation. So you take the quark, you fragment it according to whatever people have measured, and it's pretty good, okay? I mean, people have measured quark fragmentation at Hermes.
Yeah.
That's a lot.
So that would be another machinery then.
That's right. Yeah, that's not my work. That's other people's work. But quark fragmentation is people know about it. All the Monte Carlos have quark fragmentation.
So you're just coming up with an event with a W and a Q.
Right.
And even the X distribution.
Everything. All kinematics except for the
But you're not,
detail, and a quark comes out.
which is coming down
And out comes a quark.
right.
And then you do something with it.
Then you better build a quark detector.
Absolutely. All right. So
And
we,
so successful.
we did. So now we went to update. It says we want to include. We want to push this. I mean, we want to push it so to make the U and D quarks different. And for this, all you have to do is instead of predicting the photoproduction data, we're going to include the photoproduction data on hydrogen and deuterium, and that will give us the U and D quark separately. And we want to push into the resonance region. So we added more parameters, U and D quark separately, and we pushed it towards the resonance region. So we get different K factor for valence, C, DC, UC. They look different. The data gives you different K factors for them. So this is what it looks like. Red is SLAC, green is BCDMS, NMC, and the dashed line is GRV98 PDFs if you didn't apply any of those corrections out of the box. And we know that they're going to fail. They're going to fail at high X because of the target mass corrections, and they're going to fail at low X because they don't have the K factors. So if you just blindly take a QCD Monte Carlo and run it with GRV98, everything is going to be wrong at low. But if you include those corrections, things will work. And of course, Hera. Now, you say, what about this one? X equal to 0.00013. You don't fit this point here. And that's because we do fit this point. Because if you want to fit this point, you have to add a photon gluon fusion diagram that happens at those particular values. That's not included in the PDF, photon gluon fusion. But so we did when we included photon gluon fusion, it actually worked. But we don't really care much about this particular. And here's the photo production data. And you see that we've tried to extend the PDF such that they will work in the resonance region on average. Remember, this is hydrogen and deuterium, so it has all kinds of peaks and valleys for the resonances. And this is photo production resonances. Deuterium is a little more smeared than hydrogen.
So you can bring in the concept of duality?
Yes. It says right here, resonance region and quark hadron duality. So, okay, all the scattering is from quark. So if you're just a quark person like I am, who from SLAC, and everything I looked at only was W greater than 2, I figure everything is quark. But you would say, in my language, at low W, the final state interaction between the quarks gives you a nucleon resonance. But the overall strength of producing it just came from the quarks. So as far as I'm concerned, being a quark person, nucleon resonance production is just another fragmentation product of final state quarks. And if that's true, and it's called quark hadron duality, then the inelastic parton distribution curve will go on the average of the resonances. If you're really more extreme, and some people are at Jefferson Lab, very extreme, you're going to say elastic scatterings can be considered as an inelastic scattering where the quarks fragment and coalesce into one single nucleon. So this is what I call local, people call it Jefferson Lab local quark hadron duality. I mean, not only it's on average for resonances, it's on average for each resonance and the elastic peak separately. So this is really pushing things to extreme. But if quark hadron duality worked, these PDFs can be used to predict the average structure function in the resonance region. Structure functions are just PDFs modulated by a final state interaction. And in a sense, this is the kind of fits people do when they want to do gradient corrections. Most of the fits to the SLAC data when we do the gradient correction is inelastic curve modulated by some resonance structure. So it was found to work using the Nachman variable because it's supposed to be high X for Qs greater than 1, even in the region of the delta and the elastic peak and quasi-elastic peak for deuterium at Jefferson Lab. So the question, well, what about lower q square? I mean, you're pushing it below 1. And what about neutrino scattering? I mean, is that supposed to work for neutrino scattering? 2. First of all, let me show you what it looks like. So if you take the curve, you know, it averages over these resonances. And the delta is always difficult. So if you want to match a resonance model to this model, you have a region over which both models should be valid. If you have a resonance model, you should predict these resonances. So, I mean, it's only 1, 2, 3. You better predict the resonance. So, I mean, maybe you won't be able to go much higher, but any resonance model better predict this curve. So you can match onto this curve pretty simply, which is why I try to push it to higher resonance. Not because I wanted to describe it, but because I wanted the matching to be better. Yes?
I can't read it. What is the black
Yeah.
dash curve?
Oh.
What is that prediction?
Oh, this is just GRV98 without any corrections.
Just straight GRV.
Yes.
In what sense you claim that you describe it on average? Do you calculate integral for this?
No. We just use those points in the fit and let the chi-square go bad.
Just by eye.
No, not by. Let the chi-square take care of it.
The chi-square.
Yeah, but remember, I wanted just to match to, I mean, if I don't use these data, like chi-square is 1 per degree of freedom. Okay? If I use this data, my chi-square is bad because they have all those wiggles. But I'm doing it so people can match better. Okay? But I'm not really trying for, I'm saying, if you want to describe resonance, you better use another language. But if you want to use inelastic, you better use this language, and you have to match it. And this is what happens. The photo production cross-section is given by F2. So this is, take F2, predict the photo, and get the photo production cross-section for the deuterium and hydrogen, and you get this curve.
Of course, I mean, you made a good remark now. Use another language. If you are within this resonance region, and say the first 3 resonances,
Yes.
that one has up to 1600 or so,
Yeah.
you better use a resonance language also to be able to describe the decay channels correctly.
Yes, you have
You'll never get that quark fragmentation.
correct. Yes, correct. Yeah. Yes. That's why I did the easy part. Okay, neutrinos and CVC. So how do we get neutrinos? Well, CVC relates vector structure function measuring electron scattering to neutrino structure function. You just use different coupling. Electron scattering, the PDFs are weighted by the square of the charges for electron scattering. But if you go to quarks, the axial and vector coupling for quarks are equal. For but just talk about CVC. For quasi-elastic scattering where there's an anomalous magnetic moment, the CVC condition still works, but you have to use the difference between G and GM. So you can use CVC to get the vector coupling, but you don't just use this quark language. You have to use the form factor language. For delta production, I equal to 3/2, so we can predict the vector coupling for neutrino scattering from electron production, but we have another relationship because we have I equal to 3/2. So quark hadron duality for neutrino would work if you have a lot of resonances which average, but it's certainly not going to work for I equal to 3/2 resonance when you have I equal 1/2 quark. The relationship between them is not going to, the CVC is not going to give you the right one. So the delta is special because it's I equal to 3/2. But the delta is also special for another thing, another reason. Quark hadron duality, by some miracle at Jefferson Lab, seems to work for electron scattering down to the region of the elastic peak, for the neutron and the proton, and for the delta. But if you produce charge current reaction, and you do neutrino plus proton, there's no charge current process. Neutrino and proton doesn't make. You have to have a neutron. So you can't make a nucleon here. The cross-section is 0. So there goes the quark hadron duality for the quasi-elastic peak. But you go to the delta. So you can see it only has different isospin, but the local case of this duality just doesn't work for the neutrinos because something goes to a delta. So you say, well, maybe you have a chance if you need to average both quasi-elastic and delta, and some people sum up neutron and proton, and some people sum up neutrinos and antineutrinos. So there have been a lot of studies of quark-hadron duality, but they had to give up on the local part and start fudging it some other way. But I'm not doing that. Yeah, for that. I'm not doing that. I'm just telling you it's complicated. Somebody else's problem. What?
Looked at this problem,
Yeah.
she had a solution, right? So I mean, it's been done.
People have looked at it, yeah. I'm saying this is not a preview of this particular Bodek-Yang formalism. And I say that there's more than one reason not to do it. I mean, there's first principle reasons not to do it. Okay, so another way to picture of transition form factor. Another way to look at resonance productions via transition form factor. When we have many resonances, PDF should describe the average cross-section. A lot of isospin states cancel out. When you have few resonances, you better be nice to them and treat them individually as individual resonances. And then you better know what the isospin is, and Pascos has done that. Each resonance has different isospin. You better use the right CVC transition between electrons and neutrinos, and you have to worry about I equal to 3½ and I equal to 1½ background. So I would say you expect it to work maybe above the second resonance. Maybe you can push it down. Maybe I can push it to the third resonance, but only for overlap, for matching, not for actually. You better get a third resonant prediction from some other, and then match it to go above the third resonance. Okay. So axial structure function and form factors. So when I predict neutrino scattering now, and no, so far I haven't used any neutrino scattering data, I can do two things. I know for x equal to, for q squared greater than 0.2, probably vector is equal to axial. So I can just say, well, who cares about q squared less than 0.2? It's a solid cross-section there to begin with, and the vector goes to 0. And you look at q squared to 0.2. Even the inelastic structure function for the axial vector, they go down like a rock. So you're talking about this region. So okay, so and they always say, well, forget about it. Let's just make axial equal vector. For type 2, we say, well, let's be more ambitious. Let's work on the axial coupling and see what we can do. So let's have F2. Let's have the k factor different for axial and vector. So you say, well, how do we do that? So this is a type 2 model. It's not implemented in neutrino Monte Carlos. People all use type 1, vector is equal to axial, because we did that later. But now you have to bring more concepts into the picture, like PCAC. So you read theoretical paper. I think Kulagin here has done this work. Or you go to some papers. There was like CCFR tried to measure F2 at x q squared equal to 0. And you look at those papers, and you say, well, the axial neutrino structure function as you go to q squared equal to 0 in the region of the C, which is small x, appears to be non-zero a little bit. And you can either use PCAC or you use CCFR and data, and then you find out that normally the axial k factor for the vector will be q squared over q squared plus something to go to 0. But you want to add a small term to it, which is not so big. This term means that you go from 1 to 0.06. So the axial structure function indeed is not 0 at q squared equal to 0, but it's 6% of what it is at q squared equal to 1 or 2. So this is what we did for the C, because PCAC and it's been measured supposedly by CCFR. It's in one place. Axial valence. So let's go back to the axial valence. For this factor, which is on average q squared 0.18, is what average axial valence k factor is for vectors. So let me use a similar form for the axial quarks, but I'll put in a p here, and I will say that this is the only parameter I can use to adjust to get the total neutrino cross-section right. If I don't have an axial which is non-zero at q squared to 0, my neutrino cross-section is going to be a little bit low. So let me just put a little bit there. I already have 6% for the C. It turns out this is 10%. And then the neutrino total cross-section will be right. So now you have to use other information like PCSC and neutrino data but you have an idea that you didn't really make such a big mistake when you say axial equal vector. And let me show you how yeah.
Just so we can, and the plus and minus there is neutrino and anti-neutrino, or it's
No, the error. 0.18 plus minus 0.9. 50%. I put a 50% error on this.
you mean point oh nine,
0.009, right.
or did you mean point?
Oh, no, point. Oh, I missed a zero. I missed a zero there. Sorry, missed a zero for the error. Right. Yeah. I put a 50% error in all because eventually I'm going to have to tell people what is the error on the model. So I have to put an error every.
Made something.
Yes.
And it's not 500%.
So, all right. Oh well, how do you're looking at CCFR data and chorus data, all those other data. They're all on iron. What are you going to do? Well, I have to correct them. So we have this slack data for Fe over D, and the PDF I'm using are for free protons and neutrons. So to go to deuterium, we have deuterium nuclear density correction, which is an EMC effect like deuterium. So you use this curve to go from deuterium to you use this curve to go from free neutrons and protons to deuterium. Use this curve to go to, and these have been measured. This has been measured in electron scattering. So now you have iron, and you say, well, but if you want to go to carbon, then these other experiments measure Fe over C. So I'm using Fe as a standard, and these other experiments measured, gold and lead. I consider them equal, and so I have. This is the only data I have. Okay. Now we have more data now, probably in Minerva, but this is at the time. This is the only data I had. So this is what we used, because we needed this PB because chorus is a lead. For the life of me, I don't know why they use lead, but there's a neutrino experiment that used lead. So we have a lead experiment and an iron experiment. So we have CCFR, NUTEFs, CDHS, iron, chorus lead. So
Is this ratio for Iris power?
yes, corrected, yes, for neutrino. So let's, it's been nice to get corrected, yeah. Everybody does that, sort of a standard. So unfortunately, I don't have low energy neutrino data. The lowest energy neutrino inelastic data that we have is CCFR at 15 GeV. And then we go to CCFR at 35 GeV. You can put CCFR in chorus. You can take the model and correct for the iron to lead ratio. So you can put chorus and CCFR on the same plot. And if you divide by type 2 prediction. And you have to apply relative corrections, by the way, to the model if you want to use data which has not been relatively corrected. If the data has been relatively corrected, then you compare to the data. If it hasn't, you run the relative correction program and you deradiate the prediction. Anyway, so these are all been corrected for relative correction. And if you divide by 1, this includes all those axial K factor I talked about. And if so this is so if it's 1, the type 2 measurement will work. And then if you take away axial is equal to vector, then at low x, where the axial path C is different, you go below 1. So you don't fit the data as well at the lowest x point for these for the case if you don't assume some sort of axial C, which is about 6% of the C in its usual strength. So this is not really proof that you're not going to use this to measure the axial form factor. I mean, it'd be nice if we have much better data at low energy but we are pushing 35 GeV. It's not that low, but this is all we have. So it seems to work. So when it comes to the neutrino data, since it's all at high Q square, it's supposed to work. They are PDFs. What? I don't know what happened here. I lost it. Anyway, so okay, so now I was a little bit lazy and I wanted to predict the total cross section, and I didn't have the resonance model. So, but the delta is pretty simple. We know the delta cross section is. So I say above the delta we use Bodek-Yan, Below the delta, we use the delta cross-section and quasi-elastic cross-sections. We've been spending hours talking about quasi-elastic cross-section. I remember it by heart now, okay? so this is quasi-elastic delta chop Bodek-Yang. If you want to be perfect, you don't really want to put the second resonance in there from somebody else and maybe the third. But so this is what happens. So I don't really know. So I don't know if, so this is the, there's type 2 and type 1. You know, one with the axial is equal to vector, and one where I put this axial correction, and that's the red one. So I'm a little bit off right here, and if I really want to do it properly, I need to actually put a proper resonance model in. But I don't really know if I'm going to believe the proper resonance model that we have right now, because this Ryan-Segal is who knows how many years old, and who knows how good it is. So it'd be nice to improve the Ryan-Segal so we can trust it better, and then I could make this test better.
But you know about MADE, the MADE analysis, which has all that. I mean, this is the...
You have to put the axial, you have to put the axial part in here.
Yeah.
Each resonance has an axial part.
Yeah,
It's important.
So that, of course, you don't know, but you can plug it in as a sort of ansatz.
Axial is not equal to vector for the resonances.
Yeah, sure, I know.
I mean, I don't really have any. I mean, they have some axial mass and all this other stuff.
At least you would have a model which describes or which is up to date on the vector part with all the electron scattering data.
After the coffee break.
You're going to talk about that.
Well, I always thought that the resonance is somebody else's job because it's a big job, and I'm just one person. I had one student. That's it, and he's not here anymore. Anyway.
That'll be discussed after the coffee.
Okay. Okay. So I said if you want to look above W equal to 2, where the chi-square is 12, 1 degree of freedom, and try to estimate some error in the neutrino cross-section, I try to come up with errors on the neutrino cross-section that you will get from that part only. And then whatever you put in for the resonances and the quasi-elastic, and you got to put transverse enhancement or whatever, is another story. So at this point, I think this particular model, given the 50% errors I put on the axial k-factor, gives you the cross-section with an error of about 4% for antineutrinos, about 3% for neutrino, only for W greater than 2. So, okay. So scattering from bound nucleus in nuclei. Well, this is, so now we have to worry about Fermi motion, which is important in law X. We're going to measure about the EMC effect. We're going to do shadowing and anti-shadowing. And of course, we have all those other issues in the quasi-elastic, which we talked about for many, many hours. So I just want to give you a feeling what happens when you go between deuterium and iron. So this is deuterium, and this is iron for the same kinematics, 2.3 liter. The Fermi motion does a lot. So you might even think that the duality works because it smeared the resonances for you. But I don't know. This is what is known about the EMC effect on the various nuclei from SLAC. The rest of experiment I participated in, SLAC E139, and so that's what everybody uses. And it's about time, I guess, now I have to put some manpower into it. Now we have to use all the data at Jefferson Lab on different targets to actually measure the EMC effect at low Q square and measure it in the region of the resonances. And all the experiments at Jefferson Lab studying the EMC effect never looked at that region because it wasn't very interesting. They tried to go to high Q square, and all the models of the EMC effect, of course, were tested at high Q square. So, but for us, we just want to know what the EMC effect is.
So the JLab results that go down into the resonance region.
A high Q square.
EMC. What do you call high Q square?
3, 4. They're not 0.5, which is well,
Yeah, definitely.
0.25, 0.5, 0.3. This is where we want to be in this energy region. Nobody has been looking at it. But the data, we have the data from Jupiter. So we have work to do. And if you take data from Minerva, we have work to do that too. So more information will come up. So this is the future. We can analyze electroscattering data for the nuclear effects, and we can analyze Minerva data for the neutrino and nuclear correction. We can see how different they are, and it's not as easy. The other EMC effect was trivial. You took deuterium, you took iron, divided. That's it. Okay, correct for isoscalars. Here you have these resonances. So you have to take the deuterium and you have to smear it to have the iron Fermi motion, and then take the iron and take the ratio. So it's a little more complicated. You know, it's because if you just take the ratio, you're going to get resonance. Like the deuterium has narrow resonances, the iron has no resonances. You're going to have things like that, and you don't know what average to take. So you want to average it first before you take the ratio. So that's why it's more complicated. If it was easy, I would have done it.
But even for the DIS, there are differences between neutrino scattering and electron.
Yeah, I'm talking about just getting it for electron scattering. Okay. I mean, you might not have to do it in Minerva because Minerva has poor resolution, so it smears everything. But we have to smear the resonances for deuterium because they're narrow. Of course,
so Minerva has detector duality?
That's right. Okay. So where do we go from here? Well, let's talk about nuclear effect. This is the kind of data we want to have because that's the kind of data that high energy neutrino experiments produce. The doubly differential cross-section dx dy for a fixed neutrino energy. And then you do as many bins in x as you can, and as many bins in y as you can. And we want this data at lower energy. And once we have this data, then we can study the structure functions. If you have it for neutrinos and antineutrino, you can look at maybe F2 versus F3. But this is what you want to start with, to get to something like this.
Sorry,
Yeah.
I'm not understanding how we would get, I mean, you have a beautiful monoenergetic ENU at 15, what? Like, how do you extract ENU in such a,
This for CCFR? No, we have a wideband beam, and we just, well,
so is
we
this a
have-
flux average thing? Or
no. This is a bin.
Okay.
Remember, we measure neutrino energy here because we have a muon and we have calorimetry for the
Okay, so
hadron.
it's calorimetric.
So yes, so the problem is easier for the high energy experiments because they have a calorimeter. You can measure hadron energy, add to neutrino energy, correct for resolution smearing in your Monte Carlo, take a slice. And these are available in the paper. We have like 20 of those from CCFR, from Chorus, all of them produce this. So yes, it's hard for us to measure hadron energy, but we have to do it if you want to do something like that. That's a challenge. If it was easy, it would have been done.
So, is this something that,
Yeah.
I mean, obviously we'll put a lot of effort on TDK into getting calorimetric information, like that's valuable for us, but is this something that we should consider doing or at least look into, how, is it so useful for us to also try to add to this, or do you think Minerva is going to cover the phase space well?
I think everybody should add to it because, I mean, CDHS, Chorus, and CCFR were pretty much on a similar, and it was very nice to be able to compare them to each other, I mean, and these are not easy. I mean, the fact that we can have lead at CERN and iron at Fermilab complete a different experiment, different beams, and produce a differential cross-section for the same energy is nice because you don't really want to rely on just one.
Sorry if I missed the point, but is there a reason why heavier targets are preferred, or would carbon be interesting? Or
Yeah,
from like low match, for example?
sure. If they have,
If they have you, at the time of these experiments, you needed the heavier.
oh, these experiments are massive. They're 600 tons of iron.
Yeah, no, they're enormous.
The flux of neutrinos wasn't so high. No, we did it because that's all we could do.
Yeah.
What sort of uncertainty on the neutrino energy can you tolerate in these sorts of measures?
I think you have to do the analysis for specific kinematic range and to see how fast the cross-section changes with Q square and with X and Y for that kinematic regime. So if it changes fast, like at high X, then you may not be able to do it. At low X, you'll be able to do it because the cross-section is flatter. So it depends on which region. These are not easy because we don't have detectors which are designed to measure hadron energy very well.
Sorry,
yeah.
may I ask you a question? When you calculate the cross sections, you also need to know R.
Yes.
For neutrino. How
Yes.
do you know R?
Well, we use R we use R from electron scattering, and from the world analysis of electron and muon scattering, that's all we have. And the fact that I showed you that I think that the vector is very close to the actual down to q squared equal to 0.2 means to me that R vectors should be similar to R axial down to about 0.2, where things begin to totally break down. And there, R could be different. Yes, it could be different.
They are equal down to 0.2.
I'm saying using the Adler-Samuel curve, it looks like the suppression of the. I'm saying it's for F2, it looks to me like vector is equal to axial. I can't really prove that R for the for vector and axial are the same at q squared equal to, but we certainly believe it's the same for the region where the quark model works. So you know it's good for q squared equal to 2, but it's been measured down to q squared equal to half, but again it's electron scattering. Now we don't really know absolutely that R is, but R is not as F2 is the biggest contribution to the cross section. So you got so when you measure this, you don't need an R. It's a differential cross section. There's no F2, F1 here. The way you get R is you take all these energies, and then you fit R, W1 and W2 to them. You do a Rosenbluth separation. So to do this, you don't need to know R. You need to measure R from that.
When you want to extract the structure function from the
From the differential cross section. This is what you start with. So it's even not at the level of structure function yet. So it's but I think that it's not as. I think all of the problems we're talking about are soluble. I think as he said, there are a lot of electron scattering data available. So somebody should go into the neutrino generators and make sure that whatever they have in there has reasonable vector form factors, and then have the best estimate. I mean, past courses have done work on it. Other people have done work to try to put in the best axial form factors and try to get a very good resonance model. But it's a completely different field than continuum. Language is completely different. We have lots of data. All these data are fit with functional forms because we want to do relative corrections. So all these data exist. They are not separated into different isospin resonances because this resonance has several. It's not one but several. So one has to decompose the data into various resonances and use a different isospin, and then those isospin relationship have to be converted to neutrino, and then you have to assume something for the axial. So for electron scattering to do relative correction is very simple. You just fit this, and then you do relative correction. To go to neutrino scattering, you need to know all this additional information of an isospin. But I don't think we're at a stage where the resonance model even fit neutrino electron scattering data. So even before, we'd have to know about the isospin. But there's lots and lots of data. I don't know, if somebody from Jefferson should tell me if the people have done, you say Mains have done a complete analysis of all the resonances, already decomposed. And oh, yeah. Steve, you looked at this data, right? Why don't you tell him a little bit about your experience? Another talk. People have tried to take the Mainz data and put it into Genie and fix it. They tried. They'll tell you what happened.
Yeah, we have that also in Kibu.
No.
The mate is in there.
Well, the story is not over yet.
Yeah.
But they've done it. I haven't, so I can't really tell you what I know about the Mainz data.
Yeah, but that's the best available data set that we have so far for resonance physics, and they always feed in the new data that come out of JLab.
Oh, they have all the data?
JLab has done a fantastic job over the last few years to determine coupling constant, to determine decay widths of resonances, and also getting the form factors out to higher Q squared. So, I mean, this is all we have now. Up to, as you said, up to roughly W2GeV. From 2GeV on upwards, resonances overlap too strongly.
Right.
It becomes hopeless to do it in that language.
Right. So maybe this is not, I don't know if this is going to be as controversial as the quasi-elastic or not. The resonances may be. The resonances, there are many people working on resonances, and not the sparse course, other people, I don't know how much in agreement they are. But I think the inelastic part is reasonably non-controversial because it relies on data. And if you want to take neutrino data, you get the actual stuff. You do,
Well,
you,
it's a
yeah,
bit simple.
yeah,
Can I
sure.
comment on that? Okay. I was intrigued by the JLab data at W is larger than 2 GB.
Yeah.
They looked at exclusive film production. And none of the pictures or none of the predictions that were based on quark language like yours, but not using your methods, of course, were wrong. I mean, the trouble was always there was much more transverse strengths observed. For example, exclusive film production at a W of 2.4 GB, but then there were data from thermos up to 4 GB and so on.
Between polarization?
And all these, no polarization, just without polarization, just cross sections, okay?
Yeah.
And the predictions from these quark counting models were always that the transverse strength should be low, and transverse was as large as the longitudinal. So that came as quite a surprise. And it's the question, I mean, that opened up the question: when does it start to work? You know, these QCD-like methods. When before I always thought they are good enough from 2 GB on upwards. Now I'm sort of.
Well, it's one of the things that the goal of the Jupyter collaboration is to take all this data, which was done at different energy, and do an R analysis.
Yeah.
We have looked at the higher Q square greater than 1.5, for R, for nuclear targets in the resonance region, and compared with deuterium and other. And we find out that R for nuclear target is about 0.03 to 0.04, smaller than R for deuterium. And this may have something to do with the fact that the quarks leak out, and maybe the transverse momentum. We don't know, but we are working on it. So far, we found nothing wrong. That R for heavier target is smaller than R for deuterium, and it increases. The difference increases, goes from 0.03 down to about 0.04 as you go from different A's. And since R is on average 0.3, that's a big effect. So, I mean, in R, probably nothing to do with what we care about, because the error in the cross-section is going to be very small. But from an intellectual point of view, studying the EMC effect, now we're looking at, we see it's different for longitudinal than the transverse. So maybe this will help some of those models.
Yeah. I just want to point out there these intriguing JLab data around, which didn't fit so easily. But part of the discussion there centered on this question of T-channel versus S-channel production processes and things like that, which might also play a role here.
Yeah, I think in general, whether it's controversial or not, for the real deep inelastic scattering, for high Q, high W, there I think the only controversy that exists, well, that we know of up to now,
Mm-hmm.
I don't know what we're going to find in the future, is the nuclear corrections.
Yeah.
Whether one actually scales from deuterium to iron the same way with neutrinos as you do for charged leptons.
Yeah.
There is indications that this is not the same. That there is a difference.
Yeah.
You expect a difference in the shadowing region, right? Because of the difference in the coherence length of the axial. But none of this has been shown experimentally. This has all been extracted from experiments rather than actually measured. We need to measure it.
Yeah.
So the controversy is when you go down through the transition region, where you're using duality right now, and you try and predict what each of these contributing resonances looks like on that duality curve.
You know, when I did this for W equal to 2, so I don't know how many years ago it was, 5 years ago, or maybe, I was very surprised that with 5 parameters, I think to describe the entire world data, every experiment, every laboratory, every beam, with a chi-square of 1 per degree of freedom. I mean, it didn't have to work. I mean, all the higher twists were absorbed in the A and the B, And the K factor took care of all the sum rule, whatever is requirement, and it just worked. And it's very nice. It could have been complicated. You know, it could have been a lot more complicated.
So any more questions for Arie?
I have one
Please.
comment, or maybe I misunderstand this. D sigma squared dx dy. So you need a lepton energy and hadronic energy to measure in U,
That's right.
and you need a lepton energy to hadronic energy to find y. So it's kind of redundant.
No.
You need one more measurement. I think.
No.
Lepton energy and hadronic energy and something.
No. The neutrino energy is lepton plus hadronic energy, and y is the ratio of hadron energy to neutrino energy. And x has to do with the angle. Energy and y has to do with nu. Neutrino energy and nu. X has to do with q squared, which is the angle. You forgot. Yes, we have one more variable.
Lepton energy and hadronic.
Lepton angle.
Yeah, but discussing that does expose the problem. I mean, you said, you made sort of these comments about Minerva being a crappy detector.
I didn't say crappy
May or may
detector.
not be true.
I didn't say that. I said it was difficult to measure the hadron energy.
And the reason is not so much the detector, right?
Yeah.
The reason is you're trying to work at low energies.
Yeah,
So you
right.
work through those formulas, and you figure out what the relevant region of recoil energy is that you're trying to measure, you quickly realize that you are in deep trouble, right? Because you've got one or two pions and some nucleons.
I didn't want to say it was a crappy detector. It's because if you really want to measure the neutrino cross section, you will build a very fine grained calorimeter.
It's not even clear that works.
Uh,
It's a neutron problem. And you've got
A large fine
saturation,
grain.
and you've got, it's pretty tough. It's pretty tough.
Yeah. That's right. It's
Any other questions for Arie? Yes.
Would it be possible to say something about gluons using your effective core distribution?
I don't really have any handle on the gluon from a theoretical point of view. I mean, I don't have any handle as to how it should go to q squared to 0. There's no other sum rule. There's no Gauss-Fitch sum rule. There's no photo production limit.
Everything's at leading order.
What?
And everything's at leading order, so
And
you
yours.
get scattered.
So I don't really know.
If it's in the leading order, then you have the momentum summary. Maybe you can say something.
No. The momentum sum rule is violated. I'm not conserving the momentum sum rule. It's a QCD sum rule that has alpha S and higher twist corrections. I don't use it. Only the other sum rule. The data tells you what F2 is.
Is the
Only-
other sum rule any good? I mean, my understanding is that none of the sum rules ever work.
Other sum rule is exact. If it's other sum rule, it's like,
But it doesn't say that it works. It just says that in some crazy model it is exact. But this,
no, it's current algebra. It's no model.
no, that doesn't have to.
And current algebra is a buff QCD. I mean, I think a lot of theorists would commit suicide if current algebra would be questioned. But we have tested it. Pascal has tested it, and it works. And it certainly works at high q squared because you integrate the u and v, subtract them, you get 2. It's actually even built in all the PDF fits. It's a part of the constraints because it's exact. Unlike gross Laurent sum.
The thing doesn't matter though.
Right?
That doesn't mean that it works. It's just
Well, it would get dropped if it didn't work.
That's right.
PDF
well,
fitter
all
form.
others have been dropped. So.
That's,
That's pretty important.
no, that one is an anchor of current algebra.
Well, you see, we were able to use up the hour and a half.
1.5 hours? Oh, I'm glad I didn't make a longer talk.